Hello and welcome to the fourth session of Computational Fluid Dynamics by the Mr. CFD team. In this session, we are going to continue from where we left off in the last session, focusing on solver and pressure-velocity coupling. Specifically, we will discuss density-based methods here. We saw in the last session that in pressure-based methods, we have two options: segregated or coupled algorithms, and all formulations are implicit. In contrast, in density-based methods, we only use coupled methods, but for the formulation, we have two options: implicit and explicit in ANSYS Fluent. In contrast to pressure-based methods, in density-based methods, we do not use pressure or pressure correction equations. We use a system of equations, continuity, momentum, and energy to solve the simulation. However, the solver uses a new form of these equations. First, let's derive these forms of equations, starting with continuity. We write the differential form of the continuity equation. In this equation, the uppercase V represents the velocity vector, containing components u in the x direction, v in the y direction, and w in the z direction. We can convert it to the integral form by integrating over a control volume. Then, by using Gauss's theorem, also known as the divergence theorem, we can convert the volume integral over a control volume to a surface integral. V represents the volume, and we write it in this form to distinguish it from the velocity vector. And this is the face area. Okay, now for x momentum, we can start from a differential equation too. The first derivative of vor u with respect to t plus the divergence of vor velocity vector u is equal to the divergence of tau xi minus the first derivative of pressure with respect to x plus a source term for the x momentum. The stress tensor can be written in this form. It includes components like tau xx, tau xy, tau xz, tau yx, and so on, to encompass all components of the tensor. In fluid dynamics, this tensor is equal to 2 times the strain rate tensor. Specifically, it includes the first derivative of u with respect to x, 1/2 times the first derivative of u with respect to y, plus the first derivative of v with respect to x, and 1/2 times the first derivative of u with respect to z, plus the first derivative of w with respect to x. To complete this tensor, the diagonal components are the first derivative of u with respect to x, the first derivative of v with respect to y, and the first derivative of w with respect to z. Thus, this tensor helps demonstrate shear stresses in a fluid. If we denote various terms with numbers, we see that some terms repeat in specific patterns across different components. In this formula, tau xi, I can be replaced with each of the directions x, y, and z. Thus, tau xi refers to the first row of this tensor, which can be represented as a vector that includes these components. P in the first derivative of p with respect to x is a scalar. So if we define a vector pi that contains the value of p in the x direction and zeros in the y and z directions, then the divergence of the vector pi is equal to the first derivative of the scalar p with respect to x. We can use this concept to modify the x momentum formulation. Integrating the equation over a control volume and using Gauss's theorem to convert the volume integral to surface integrals allows us to derive the equation for the x momentum. We also use this relation to transform the scalar pressure into a vector form. Additionally, the divergence in the integrated form over the control volume can be changed to an integral over the control volume surfaces. So if we rearrange this form and collect all the surface integrals together, we can derive this formulation for the x momentum equation. To obtain the y and z momentum equations, we can simply replace u with v or w for the velocity and adjust the pi vector to py or pz, as well as change tau xi to tau yi or tau zi. This includes the source terms in the y and z directions. No, we can write the differential equation for energy. The first derivative of vor E with respect to time plus the divergence of rho VE is equal to the divergence of K, the thermal conductivity, multiplied by the gradient of E plus additional terms. Specifically, we can add the energy dissipation of the fluid because of shear stresses, which is the divergence of tau ijvj, minus the energy transferred due to pressure gradients, which is the divergence of PV, plus the volumetric source term. In this equation, E represents the total energy per unit mass, and K gradient of E corresponds to the heat flux Q. The term tau ijvj can be split into components as tau xxu plus tau xyv plus tau xzw in the I direction. This can be extended to derive similar expressions for the J and K directions. The vector PV has components such that in the I direction its value is PU, in the J direction its value is PV, and in the K direction its value is PW. By integrating this over a control volume and using Gauss's theorem to convert the volumetric integral to a surface integral, we can reach the desired equation for energy conservation. So we derive the formulations for the continuity, momentums, and energy equations. These equations are valid for steady or unsteady flows, and they can accommodate both constant and variable density and viscosity. In the energy equation, E represents the total energy, and we can also derive the formulation for the total enthalpy. The total energy E is equal to the total enthalpy H minus pressure divided by density. The total enthalpy H is equal to the static enthalpy plus the kinetic energy per unit mass, half velocity magnitude in the power of 2. For calorically perfect gases, the static enthalpy can be expressed as Cp times T, where Cp is the specific heat at constant pressure and T is the temperature. If we look at the system of equations, all the equations have the same format. For example, if we consider the unsteady term for all equations, we can write a 1/5 matrix denoted by W, which represents the unsteady term. Furthermore, we can define F for the flux terms, G for other directional fluxes, and H for the source terms. Thus, we can write the system of equations as follows. The first derivative of the integral of W over the control volume with respect to time, plus the surface integral of F minus G over the control volume surfaces, is equal to the volumetric integral of the source terms, H over the control volume. This formulation shows how the changes over time, unsteady terms, fluxes through the surfaces, and sources within the volume contribute to the behavior of the system. The Navier-Stokes equations, as expressed here, become very stiff at low Mach number due to the disparity between the fluid velocity and the sound speed. This is also true for incompressible flows, regardless of the fluid velocity, because sound travel infinitely fast in an incompressible fluid. The numerical stiffness of the equations under these conditions results in poor convergence rates. This difficulty is overcome in ANSYS Fluent's density-based solver by employing a technique called time derivative preconditioning. This has the effect of rescaling the sound speed of the system of equations being solved in order to alleviate the numerical stiffness encountered in low Mach numbers and incompressible flow. Derivation of the preconditioning matrix begins by transforming the dependent variable in equation from conserved quantities W to primitive variables Q using the chain rule as follows. The matrix W, as we defined earlier, is a 1 by 5 matrix consisting of there U, there V, there W, and there E. Similarly, Q is a 1-5 matrix containing P, V, W, and T. The derivative of W with respect to Q is a matrix where the derivative of ver with respect to P, denoted as ver P, which represents the partial derivative of density with respect to pressure at constant temperature. The derivative of there with respect to U, V, and W is 0 because density does not change with changes in velocity. The derivative of ρ with respect to T, denoted as ρ T, is the partial derivative of density with respect to temperature at constant pressure. Similarly, for ρ U, the derivative with respect to P is ρ P U. The derivative with respect to U is ρ. The derivatives with respect to other velocities, V and W, are 0. The derivative with respect to T is ρ T U. You can extend this pattern to compute the derivatives for ρ V and ρ W. For the total energy, there E, it can be expressed as ρ multiplied to H minus P divided by, where H is the enthalpy. Upon differentiating with respect to pressure, the derivative ver HP with respect to P simplifies to ver H minus delta, where delta is 1 for ideal gases and 0 for incompressible flows. For the derivative of total energy with respect to velocity, U, we can consider the partial derivation of ver H minus P with respect to U. As discussed earlier, the total enthalpy H is the sum of static enthalpy and kinetic energy per unit mass, which can be expressed as H plus half of U in the power of 2 plus V in the power of 2 plus W in the power of 2. The derivative of the static enthalpy H with respect to U is 0, since H is not a function of velocity. For the kinetic energy part, we take the partial derivative of ρ U in the power of 2 plus V in the power of 2 plus W in the power of 2 with respect to U minus partial derivative of pressure P with respect to U. The partial derivative of pressure with respect to U is 0, given that pressure does not directly depend on velocity in this formulation, and similarly, the derivatives of V and W with respect to U are also 0. Thus, the formulation becomes ρ U. A similar process can be followed for the derivatives of nor E with respect to V and W, resulting in nor V and nor W respectively for those components. Now let's define the derivative of nor E with respect to temperature. We start with the partial derivative of ver H minus P with respect to T. We can split this into two terms, partial derivative of ver H with respect to T minus partial derivative of P with respect to T. The derivative of pressure with respect to temperature is 0. For the first term, we can apply the chain rule, partial derivative of ρ with respect to T times to H, plus ρ times to partial derivative of H with respect to T. The total enthalpy H is equal to the static enthalpy plus the kinetic energy per unit mass. The static enthalpy H is expressed as CPT, where Cp is the specific heat at constant pressure. Thus, the derivative of static enthalpy with respect to T is Cp. Therefore, the derivative of ρ with respect to T is denoted as ρ T, leading to the total derivative of ρ E with respect to temperature simplifies to ρ TH plus ρ Cp. Now the matrix is completed. The choice of primitive variables Q as dependent variables is desirable for several reasons. First, it is a natural choice when solving incompressible flows. Second, when we use second-order accuracy, we need to reconstruct Q rather than W in order to obtain more accurate velocity and temperature gradients in viscous fluxes and pressure gradients in inviscid fluxes. And finally, the choice of pressure as a dependent variable allows the propagation of acoustic waves in the system to be singled out. We precondition the system by replacing the Jacobian matrix derivative of W with respect to Q with the preconditioning matrix, so that the preconditioned system in conservation form becomes what is presented here. Here, the parameter theta is given by 1 over ur minus rho t divided by rho cp, where ur is a locally chosen reference velocity. This reference velocity, ur, is selected to ensure that the eigenvalues of the system remain well conditioned with respect to both convective and diffusive timescales. The resultant eigenvalues of the preconditioned system are given by. Here, the relations for the u prime, c prime represented with the formulas of alpha and beta. Consider an ideal gas where the equation of state is given by ρ equals to P divided by RT, where ρ is the density, P is the pressure, R is the specific gas constant, and T is the temperature. We can then find the derivatives of density with respect to pressure and temperature. The derivative of density with respect to pressure is 1 over RT. The derivative of density with respect to temperature is minus P divided by RT in the power of 2. The specific heat at constant pressure, Cp, is given by gamma R divided by gamma minus 1, where gamma is the heat capacity ratio, specific heat ratio. By substituting the values for rho P, rho T, and Cp into the formulation of Beatty, we can find this relation. We can perform some simplifications that lead to beta is equal to 1 divided by gamma RT. This is the inverse of the square of the speed of sound, c, in an ideal gas. Considering the speed of sound as the reference velocity, then alpha would be 0. If we replace these values back into the original relations, the speed u prime is modified to yield u, the flow velocity. The two eigenvalues or characteristic velocities become u plus and minus c. These eigenvalues reflect the fundamental wave speeds in the system, one moving upstream at u minus c, and the other moving downstream at u plus c. Now consider a scenario with very low velocities where ur, the reference velocity, is 0. In this case, alpha would approach 0.5 due to the ideal gas relation, as beta would be inverse of the square of the speed of sound. C prime would be half of the flow velocity, u, would similarly be half of u. The eigenvalues or characteristic speeds of the system then simplify to 0 and u. Now, assuming constant density, ρ, so that both ρp and ρt are 0, the system becomes independent of the values of ur, the reference velocity. In such a scenario, regardless of the value of ur, alpha becomes 0.5. Consequently, as long as ur is close to u, the system's eigenvalues generally remain around the order of u from low speed to high speed velocities. Thus, the eigenvalues of the preconditioned system remain well conditioned at all speeds, since the preconditioning has already destroyed the time accuracy of the equations, and we will not employ them in this form for unsteady calculations. For unsteady calculations, an unsteady preconditioning is available when the dual time stepping method is used. Now let's derive the fundamental formulation to the row scheme and mathematical basis for computing numerical fluxes at cell interfaces in computational fluid dynamics. Regarding the general form of the conservation equation, consider the differential form. It involves the partial derivative of q with respect to time plus the derivative of the convection term with respect to x. This convection term can be expressed as a function of q, and with chain roll, we can replace the gradient of f with gradient of q. The derivative of f with respect to q results in a Jacobian matrix, denoted as A. In general, since conservation equations can be nonlinear, the matrix A is not necessarily linear. However, we can approximate it using a locally constant matrix, A tilde, that satisfies certain conditions. The mapping from the vector space Q to the flux vector space F must be linear. If we are considering fluxes at an interface, and if QR and FR represent the values at the right cell of the interface, and QL and FL represent the values at the left side, then as QL and QR approach the interface value of Q, A tilde must approach A. The product of A tilde and the difference in Q across the interface, QR minus QL, must equal the difference in the flux, FR minus FL. This condition ensures that A tilde satisfies the Rankine-Hugoniot shock jump condition, and the eigenvectors of A tilde must be linearly independent. These conditions ensure that the model accurately represents the behavior of the system at cell interfaces within the numerical method framework being used. The matrix A tilde can be diagonalized. The matrix A tilde can be expressed as A tilde equals to S lambda inverse matrix of S. Here, lambda is a diagonal matrix of eigenvalues, and the eigenvalues are U minus A, U, and U plus A, where U is the fluid velocity and A is the speed of sound. In our notations, the speed of sound represented by c, so the eigenvalues become U minus C, U, and U plus C. The matrix S contains the right eigenvectors, while S minus 1 contains the left eigenvectors. We can define lambda negative and lambda positive, where lambda negative is lambda minus the absolute values of lambda divided by 2. This means replacing the positive eigenvalues with zeros, and lambda positive is lambda plus the absolute values of lambda divided by 2, replacing the negative eigenvalues with zeros. To determine the flux F at the interface of two cells, using either left or right fluid states, we calculate, for the right state, F is equal to F at left cell plus S, lambda negative, S minus 1 multiplied a difference of value of Q at right and left cells. For the left state, F is equal to F at right cell minus right eigenvector matrix multiplied to lambda positive and left eigenvector matrix multiplied to Q right minus Q left. By averaging these two expressions for flux at the interface, we obtain F is equal to average of F at right and left cells plus S lambda negative, S minus 1 minus S lambda positive, S minus 1 multiplied to Q right minus Q left. This parenthesis can simplify to this form. And by replacing lambda negative and lambda positive, it will result S absolute of matrix lambda S minus 1. By calculating the necessary expressions, the matrix A for the X component can be formulated. In this matrix, K represents the kinetic energy per unit mass. Additionally, the right eigenvector matrix and the left eigenvector matrix are presented as shown here. The matrices A, S, and S minus 1 must be formulated using values at the interfaces. These interface values are typically computed as some form of average between the properties of the right and left cells. Consequently, the relationships that define the interface values based on the properties of the right and left cells are presented here. For example, let's derive the value of U tilde based on U and R at the right and left cells. We start with the expression for delta der U, which equals R delta U plus U delta der. For the momentum equation, the expression delta der U in the power of 2 using the chain rule equals 2 der U delta U plus U in the power of 2 delta der. If we use the first relation, der becomes delta der U minus U delta der divided by delta U. Now, we can replace this relation in our earlier expression. Delta rho U in the power of 2 equals 2U delta rho U minus U delta rho divided by delta U times delta U plus U in the power of 2, delta rho. In the first term, the delta U cancels out. Each delta can be replaced with the difference between the right and left cell values. Thus, delta rur u in the power of 2 can be written as re r u r in the power of 2 minus rur l u l in the power of 2 equals 2. Simplifying further, after rearranging, the expression becomes dor r minus rur l times u in the power of 2 minus 2, rur r u r minus rur l u l times 2u plus rur r u r in the power of 2 minus rur l u l in the power of 2. Note that this is a quadratic polynomial in u. To find u, we can use this expression for the first root of the equation, substitute the coefficients into the quadratic formula. Here, b is minus 2 rur r u r minus rur l u l. Further simplification and cancellation yield a form where the square root and factors simplify terms such as ur minus ul in the power of 2. In both the numerator and denominator, simplification using algebraic identities leads us to the final expression for u tilde. This expression draws on the square roots, dor L minus square r, and terms cancel out appropriately in the numerator and denominator. The exact formulation for u tilde is outlined. By replacing this relation of u tilde in the quantity delta ver u, we can derive ρ tilde. Further, by applying these in delta ver hv, other variables like h tilde can be found. As an exercise, you are encouraged to derive these relations yourself. In the context of advection upstream splitting scheme, consider the matrix F, which is the convection matrix. This matrix contains terms ρ v, where v is the velocity, ρ uv plus p, ρ vv plus p, ρ wv plus p, and ρ ve plus pv. Here E can be replaced with H minus PV, making it equal to ρ VH plus PV minus PV, which results in the cancellation of PV. In the advection upstream splitting scheme, AUSS, the convection term is split into FC and FP. Where FC consists of terms ρ V, ρ UV, ρ VV, ρ WV, ρ HV. The pressure terms are grouped in FP. FC is marked as dependent on the advection Mach number with m times the vector matrix that includes ρc, where c is the speed of sound, ρuc, ρvc, ρwc, and ρhc. Now, consider a single cell where information can propagate in two directions. positive and negative, with two neighboring cells by an interface. The interface properties are influenced by the positive Mach of the left cell and the negative Mach of the right cell. The average Mach number, m½ is computed as the average of the positive Mach on the left and the negative Mach on the right, as discussed. If the advection Mach number is negative, the flow is in the negative direction, and the values for this flow direction should be taken from the right cell. Conversely, if the Mach number is positive, values should be taken from the left cell. For subsonic flows, the positive or negative mark is computed as 1/4 m plus minus 1 in the power of 2. In supersonic flows, it is computed as m plus minus absolute value of Mach divided by 2. In supersonic conditions, information travels predominantly in one direction, resulting in the negative mark being 0. Conversely, in subsonic conditions, information can travel in both positive and negative directions. This method allows the scheme to determine which cell's properties influence the interface, depending on the direction and magnitude of the Mach number, ensuring accurate simulation of the flow dynamics across cell interfaces. Similarly, the Mach number p can be calculated using these relations. For subsonic conditions, the relation is as follows. And for supersonic conditions, the relation is given by a different equation. In supersonic flows, the positive pressure information is conveyed with P, while in the negative direction, the information doesn't propagate, making P negative equal to 0. By incorporating these relations into the formulas for F, it becomes F equals to advection Mach times the right or left matrix of advection The pressure, Fp, is defined as the sum of the positive pressure from the left cell and the negative pressure from the right cell. This approach ensures that each component of the flow is appropriately influenced by the prevailing conditions in adjacent cells and that the pressure contributions are accounted for in the flux computations. Now we derive the formulation for the schemes of the upstream splitting scheme, USS, and also the row flux difference scheme. Both of these schemes can calculate values in either an explicit or implicit manner. As discussed earlier, in the explicit formulation, only the values at the one cell are used for the next step, with all other values imported from the previous iteration. Thus, delta Q at this iteration is equal to alpha I inverse gamma delta T R in the power of I minus 1, referring to the changes from the previous iteration. In steady-state or unsteady simulations, delta T appears in the equations. For steady-state simulations, this process continues until the variables converge to a steady solution. The relation for R is presented here. As discussed, in the explicit method, the values for F and G are taken from the previous step. After calculating delta Q, Q at the next iteration can be solved. In this formulation, delta T is equal to 2 times CFL times V, where CFL is the Courant number, V is the cell volume, and in the denominator Lila max, the maximum local eigenvalue, and AF is the area of the face. In the implicit discretization method, all values are taken from the next iteration, which makes them unknowns. Therefore, we replace F and G with the formulations derived earlier and replace delta Q accordingly. By factoring out common multiples of delta Q, the reformulation will be as follows, where D and S are defined here. This creates a system of equations that can be solved. By calculation, we can determine delta Q. In the next iteration, Q is computed as the previous Q plus delta Q times alpha, where alpha is the under-relaxation factor. In this session, we derive the basic formulation for the density-based solver and velocity coupling. Make sure that you are comfortable with this derivation. In the next session, we will cover the discretization methods for any property implementation. After that, we will solve some examples. So stay with us.